Well, good afternoon, folks. I'm Wenhao Wang from Yale University. I'm a first-year PhD student advised by Fan Zhang. And today I'm going to present our work on mechanism design in ZK-Rollup program market. And this is, oops, what happened? Okay, so this is joint work with Lulu, Aviv, Fan, Ben, and Benjamin. So first, let's remind ourselves of this fact. ZK applications need program markets. So nowadays, we have a lot of ZK applications. For example, zero-knowledge decentralized identifiers, zero-knowledge virtual machines, ZK-Rollups, and they all are facing a problem. That is, zero-knowledge proofs are very costly to compute. And it's typical that these ZK applications will assign the job of generating such ZKPs to provers. And the idea is that instead of having only one prover generating the ZKP, we can have many provers distribute the job. So these provers may have their own capacities, own cost of proving, and they act as the supply side of the prover market. And these applications and the users of these applications may also have valuations of their transactions, their programs, and they act like the supply side, demand side of the prover market. So let's narrow down our scope for a little bit. Let's talk about prover market in zero-knowledge rollups. And we say here, the mechanism design problem for ZK prover markets is challenging. It's a challenging matching problem because of these facts. So let's firstly focus on what's the dynamic of between users and provers in ZK-Rollups. So users, basically, they post their transactions on the rollup and offer their fees for the transactions, while the provers are willing to supply proofs for such transactions at a cost. And also in ZK-Rollups, for efficiency considerations, user transactions needs to be batched instead of being proved one by one. And also, we have that users and provers are strategic, so they are willing to bid optimally to optimize their revenue. So, given this problem, we have a Strongman mechanism. So in the Strongman mechanism, the users basically submit their bids, which are their transactions and the fees they are willing to pay for their transactions, while the provers will submit their bids in the form the proof generation capacity each prover will have, and the unit cost for generating a proof. So the Strongman mechanism is fairly simple. It basically looks at this. So the mechanism greedily includes the highest fee transactions and the lowest cost provers into each round until the prover cost cannot be covered by the users. Here we omit the limitation that this implies the transactions are ordered by fees, but let's just omit that limitation so far. So let's look how this mechanism will pay the provers. So basically, the provers get paid the second price, or more strictly, the weekly payments. So say if there are two provers, the first prover, the lowest cost prover actually gets paid the second lowest cost in this Strongman solution. And there may be some difference in the fees collected from the users and the rewards that's actually distributed to the provers, and we simply burn that difference in the Strongman mechanism. So let me give you an example. So let's see, there are three types of different transactions in the prover market. So there's one transaction at a valuation of 9, 5 transactions at valuation of 5, and 10 transactions at valuation of 1. And we also have two types of provers. Well, the first prover is willing to prove 10 transactions at cost 1, while the second prover is willing to prove 10 transactions at a cost of 5. So if everyone is honest, well, if everyone is very merry, so here's what's going to happen. What's included in this round is actually one transaction at valuation 9, 5 transactions at valuation 5, and 1 transaction at valuation 1. So this is the maximum number of transactions that can be included in this batch. While the prover gets selected is the first prover because of this, it's the lowest cost prover and it's paid the second price. So it's actually paid 5, which is the cost, unit cost paid to the prover, and 7 is the number of transactions. However, this example has a collusion problem, which can be demonstrated here. So actually, the second prover and one transaction at the cost of 5 can collude with each other. So the second prover can bid 4 instead of its true cost 5. And the user, the malicious user, can bid 2 instead of 5 as well. So in this case, what is going to happen is that the joint utility of this colluding user and colluding prover will increase by 3 because this user transaction will now still be included in this batch, but it pays less. Okay. So why I want to show you this Strongman mechanism because we previously think it may satisfy these desired properties. Informally speaking, these properties are respectively efficiency, incentive compatibility, and option agreement proofness. Let me explain. Efficiency in the sense that the proof of market should be able to prove as many transactions as possible, and incentive compatibility in the sense that the mechanism should encourage each actor to behave honestly. And option agreement proofness in the sense that no collusions between users and between provers can increase their joint utility, so they cannot act maliciously by forming a collusion. So, however, there are problems with this Strongman mechanism, and we asked the question, how can we design a mechanism to satisfy these properties? So the first problem with the previous Strongman mechanism is that the payment to each prover is dependent on other prover space in the Strongman solution. So let's recall, so in the Strongman mechanism, we actually pay the winning prover the second price, the victory payment. So it's not separable payment rule. So this may cause some problems. For example, if the not winning prover can change their bid for a little bit, then it can change the allocation, who is winning and who pays what amount of money for the entire round execution, which is not what we want. And this may cause some collusion problems. So the idea to solve this problem is that we use a separable payment rule for provers. Well, the second problem for the Strongman mechanism is that there are some fee burns. So let's recall, so it's actually separated how we collect fee from the users and how we distribute the reward to the provers. And this Strongman mechanism actually burns if there is difference between them. So this is not optimizing the social welfare. And since the social welfare is not optimized, some collusions formed by users and provers may be strategically to extract this burnt fee, which we don't want either. So the idea for this to solve this problem is that we optimize social welfare by removing burning for all within all mechanisms. And the third problem with the Strongman solution is that the prover can include non-winning users to win additional profits through option agreements. So I'm not going to get into detail, for example, for this problem, but the idea we solve this problem is that we can cap the number of transactions that can be included in each round of mechanism execution by adding a capacity parameter. So based on these three observations, we present our mechanism proofy. So let's see how it works. So basically, on a high level, proofy assumes that we have a fixed capacity parameter C in the number of constraints for each round of the mechanism execution. And it will select transactions with the highest value up to that capacity limit. It's like Ethereum before the EIP 115.59 upgrade. And after we select the user transactions, how do we pay the provers and select the provers? So basically, this mechanism simply calculates the average fee of the selected transactions, and all provers with cost less than average fee may be profitable to prove this transaction, so they join a lottery pool. And this mechanism then randomly select provers in the pool until all transactions can be proved by some prover. So about this proofing mechanism, we actually can show that it can have some good properties that we desire. Firstly, we can show that proofy is incentive compatible for the users. And secondly, we also can show that proofy is incentive compatible for provers if we assume that no Sybil attacks can happen. So in Sybil attacks in the sense that, recall that in proofy mechanism, all provers may join a lottery pool, but the Sybil attack problem is that some prover may create a lot of copies of itself and therefore increase its chance of winning. But however, if we assume that no Sybil attacks will happen, we can show that it's also incentive compatible for provers. And we'll discuss our potential ideas to forestall Sybil attacks in later slides. And it also has some other nice properties, and most importantly, it is option agreement proof, in the sense that no correlations between some user and some prover can increase their joint utility. So this is a property we want to achieve in the Strongman mechanism, but which we couldn't, but it can be achieved and proved now. Still, this proofing mechanism has some limitations I want to show you here. So firstly, it's not collusion resistant for provers. So let's give you an example. So let's think in the worst case, all provers in the prover market can collude with each other, and they will be strategically to extract the most amount of revenue from the users, which we don't want to see. So our mechanism is not resistant to this type of attack. And we also show examples. We also have shown examples that it's not collusion resistant if some parts of the provers collude with each other. And regarding efficiency, we observed that the efficiency of this proofing mechanism is highly dependent on how we set this capacity parameter C. And the efficiency is suboptimal if the capacity parameter is set too low. So we may need to find a way to adjust the capacity parameters to accommodate the market conditions in the zero-knowledge prover markets. Okay, so let's look at the discussions, open questions. So we have 4 points here. Firstly is how do we prevent the Sybil attack, which may exist in the proofing mechanism. So we have 2 different ideas. One is from system level design. We can have registration for provers. So the prover must register themselves before joining the prover markets. So this can in part mitigate this Sybil attack problem. And in a mechanism design level, we can have some proof of stake when we do the lottery draw. So each prover, in this sense, will be drawn with probability proportional to how much stake it has in this network. The second discussion point I want to address is how do we adjust the capacity parameter? Well, we observed that the optimal capacity parameter is actually the sum of prover capacity in the lottery pool, but we still need to find a way to adjust it, so we leave it as an open question to you. And the third discussion is how do we mitigate collusions among provers? So as I said, the full collusion among provers is always a problem for any kinds of mechanism because they can always bid strategically with each other to extract maximum value from the users. One way we think to mitigate this is actually we can set a default prover either run by some third party or run by the ZK-Rollup itself. It has reasonable price, reasonable capacity, which means that the user can some parts of the user transactions can always get through with reasonable price. The first point is how is getting full incentive compatibility. So let's recall our goal of designing a mechanism for ZK-Rollup prover markets. The final goal is actually to have a mechanism which is incentive compatible for both users and provers, also proof, and collusion resistant for provers. So how to design such mechanism is an open problem now. And the takeaway of today's talk is that proofy is a transaction fee mechanism for ZK-Rollup prover market that aims to encourage low-cost provers and forestall attacks. And our paper, Mechanism Design in ZK-Rollup prover markets, which has the same title, is online, and you can scan this QR code to get access to it. And what you will find in this paper is our models of prover market in ZK-Rollups, our model of threats, and the desired properties of a prover market mechanism. And we state in more details the proofy mechanism and analyze the properties, and also discuss in more details open questions and directions to explore in the future. So if you have any ideas of how to address open problems, we're happy to chat after this talk. Thank you.
Thank you, Wenhao. Do we have any questions? Oh, over there. Just wait 1 second for the mic, please. We gotta get that audio on video. There in the middle.
What would happen if there were a number of 0 bits?
A number of 0 bits, you mean the prover wants to prove some transactions at 0 cost?
Yes.
Well, actually what we show that the prover in this mechanism will actually choose to bid their costs, truthfully. So in reality, in my point of view, I wouldn't think there would be provers actually has 0 cost, right?
No, but for example, in Mina, it's currently happening where they're doing proofs for free.
Then maybe they will get selected as some round of the execution of the mechanism. And if the fee is very low, which is below their actual cost, then they will earn a negative revenue in such rounds.
So did I understand correctly that the price that ends up getting paid to the prover is not the same as what they bid?
Right. the mechanism will actually select the provers. So what we have in proofy is actually the mechanism will select the provers who is profitable to prove the batch of transactions. So if they bid dishonestly, such, for example, they bid maliciously low cost, they may lose in such ways.
We have to go to the next talk, I'm afraid. If you have more questions for Wenhao, please feel free to hook up with them afterwards. Thank you very much, Wenhao.
Thank you.